So, okay, great. So welcome everybody to this week's Intercats seminar. We've got the pleasure of hearing from Moritz Schauer of the Chalmers University of Technology in Gothenburg and the University of Gothenburg, who's going to be talking about some nice work he's done on bidirectionality and optics in filtering and stochastic processes. He said he doesn't mind being interrupted with short questions or longer questions. Of course, we'll have time at the end. So please, Moritz, take it away.
Yeah, thank you for having me. So this is joint work which started about maybe now 2 years ago, and I have to right away start with that I'm certainly an outsider what concerns category theory. So I've also not made my talk very heavy on that side, and I'm trying to stay a bit in the problem domain. And I want to talk about how bidirectional structures naturally turn up in inference and stochastic optimization problems. And so this is joint work with Frankfurt and Bellman, TU Delft, also in the audience, and recently got a bit of nice input from the from our Gothenburg reading group on optimal transport, and I'm using a bit of the material there also to illustrate what this is about. So my talk will, I need a bit of infrastructure to talk about what I want to talk about. So I thought that before starting off, let's start very simple. So to start very simple, I just take a Markov chain with values in finite sets. So the x0 is my random variable corresponding to the starting state of the Markov chain. And if I want to characterize the starting state, then this is a discrete probability distribution. And I can just consider the row vector Q0 of starting my process x0. And as it's Markov, the second ingredient to describe the process I need is the transition matrix. And I say that I have for each transition from time s-1 in state I to some state j at time s, I have a transition matrix which gives me the conditional probability to go from I to j. And as it's total, if I sum over the j's, I get 1. That means that my matrix PS is a stochastic matrix. And with these transition matrices, I have started prescribing the marginal distribution of my state x0 as q0. But then this implies that the marginal distribution of x1 at time 1, that will be the row vector Q0 times the stochastic matrix P1. And likewise, recursively, I get my marginal distribution at time 2. Again, applying a transition matrix, the stochastic matrix P2. And likewise, I want to consider the conditional probabilities to end in a certain state. So I'm fixing a time frame, a horizon t, number t, and a state L. And then I'm considering the probability to get from my current position at time s, so the next transition will be s+1. So from time s into state L, and the transition law will be the matrix product, the product of the tail sequence of transition operators. And as t and L is fixed, I'm just considering this as a now column vector, and I call it HS. But you might want to give it a different letter like L for likelihood or whatever. So then where does my bidirectionality come in? So I have this simple setting where I observe the process xt at time L, and I'm considering the marginal posterior, so the posterior of the marginal distribution of xs given the observations for some s smaller than t. And then that's just Bayes' theorem, so I'm looking at the posterior distribution. That's the distribution unconditional, that will be just the marginal distribution, which is QS, as I have already defined it on the previous slide. And I'm getting the conditional distribution to end up in my observation at time t in observation L. That will be the vector HS. And then I have characterized my conditional distribution as a product of QS, HS in I, and I'm using a comma to indicate that this is a column row vector and this is a column vector. And the normalizing constant is then just the dot product or the inner product of these two vectors. And if you remember that QS is the push forward of the Q0 times the matrix product defined recursively forward in time, and the HS is the pullback of HT, or the product with the tail sequence defined recursively backward in time. And if I want to seed the backwards recursion, I'm seeding it in HT, which is just a unit vector which has 1 in the actual observation. So that is for the marginal distributions, but later on I'm mostly concerned with the conditional distribution of the entire process. And to have it simple, right now I'm considering the evolution of the conditional distribution. So if I'm talking about the conditional marginal distribution and I'm giving it the name pi s, then I can write down, just by looking at the previous slide, what the evolution law for this sequence is. And this will be that I'm getting my pi s as row vector times matrix product of pi s minus 1, so my marginal conditional in the previous state, plus times stochastic matrix. And this stochastic matrix is P star, which is my matrix PS. But then each column weighted appropriately and divided by something which comes from just evaluating the previous slide, but it also is exactly what will make P star into a stochastic matrix. So here you have seen a bit how if I have information in the future and I'm computing the likelihood recursively backwards in time and the marginal distribution recursively forward in time, that and then I can say something about the conditional process. So the process X was Markov. You will be convinced later that if the process is Markov, then also the conditional process is Markov. And the law of the conditional process corresponds to the P star. So there's a bit of machinery here. And I would like to consider one of these transitions, PS, so just calling it P on this slide. And then there is a backward element where I'm applying P to H to get PH, that's the backward recursion. But then I'm also moving forward on the conditional marginal. I'm applying P star to the pi. And I've made P star blue because it depends on information from the backward path. So if you remember the definition of P star, then it's the changed transition matrix P, and it's changed with weights H, normalized with weights PH. So yeah, you're seeing where this is heading. So then it's maybe nice to see the other side, how this looks in a computational setting. So here I have written a little program which generates me a Markov chain, saves all the states in the vector XS. And I've instead of looking at the evolution of the law, I'm directly sampling the Markov chain. This is not very idiomatic Julia code, but I'm written this sampling function to indicate that it takes a random number argument, a current state X, and a transition. And the transition is taken from the sequence of transitions and gives me then the state in the next state. So if X is the value of capital X s minus 1, then the return value will be a sample from the conditional distribution of x s. And I'm just using the random, I'm returning the random number generator argument to indicate that this is kind of a monadic construction. And now I have my generator program. So how does it look like if I want to consider the conditional program? So I'm defining, I had this machinery, so let me define it here. The one part of the machinery that was the backward pass, and it just computes, taking the argument p and h, it computes the matrix product p times the column vector h. But I also mentioned that because in the forward pass, there's a dependence on the backward pass, I'm packaging the information I need in the forward pass in this message m. And I'm trusting the environment that if I'm calling the forward pass, that I will receive this argument m. And I unpackage it, it gives me the p times h and the h. And with that, I'm able to compute the p star. Or if you look carefully, this is the corresponding row of the transition matrix, because I know that I'm in state X, so I don't have to compute the entire matrix, and I can just compute the corresponding row directly. And then I'm returning a sample. So this will be the transformed function. I had the generator, and now I'm looking at the function, how it looks like if I apply the machinery, let's say. So I'm getting as arguments the sequence of transition kernels, the initial starting point, and an h which corresponds to the information I want to condition on. So for example, in this example, I'm just conditioning on the final value. And now I'm moving backwards in time, so reversed along the sequence of transition kernels or transition matrices, applying my backwards operator, saving the messages in the list. And when I've done that, then I'm moving forward. And now I'm moving in parallel along the sequence of P's and the sequence of messages, applying my forward scheme. It receives my current state, my transition, and my message M. I need to go from P to P star and pushing the samples into the vector X. That gives me a sample of the conditional process, given the observation of the trajectory at time capital T, if you want. It's implicit in the length of the PS vector here. So now this is a bit of the flavor of the talk. So let me give a short overview. I will put this in a category theoretic setting. Then I talk about the core idea, the H transform, which is the transform from the, in the example, transition matrix P to the transition matrix P star. Talk about the bidirectionality there, connected a bit to optics. And then I have a little bit of time, so I can not do everything, but I would like to try to connect it to optimal transport. And then we have two important concepts where this is turning up, so we can now do a Bayesian inference and optimal transport with this. So let's see. So I'm in borrowed stoch. I have as object measure spaces, which are I'm using mostly the letter S, capital S and capital T for that. And each of them is a state space with a sigma algebra. And these measure spaces, they come with a Cartesian structure where I can compute a product measure space by the product set times the product sigma algebra. One special space I also would like to have is a space where the state space only contains a single element, and then the sigma algebra will only contain the empty set and the set with the element itself. And one can treat it a bit informally as the unit of the tensor product of the spaces. So now I have my objects. I talk about the morphisms, the arrows of the category. These are the Markov kernels. So what is a Markov kernel? A Markov kernel is just a, essentially it's a measure, a Markov kernel from S to S prime, these are the measure spaces, it's essentially a measure on S prime parameterized by elements of the state space of S. And if you're a bit careful, then it's measurably parameterized, but that's the key message. So for later reasoning, I have an example, but it essentially just gives an example of a Gaussian transition kernel of a random walk, which has unit increments. There's a question?
Yes, sorry. Wouldn't arrows in Borel-Stokes usually be maps into the unit interval corresponding to cumulative distribution functions?
Should be just I think so. Let's keep it like this.
Okay, yeah. So densities.
No, these are not densities. These are Markov kernels. So it really measures, conditional measures.
Okay, so they're not probability measures yet.
So I will need a bit of infrastructure of sequential composition and parallel composition. Let's do the parallel composition. First, it's also a good moment to introduce my notation for defining new kernels. So I have a kernel, Markov kernel B and a Markov kernel B prime from S to T and S prime to T. These are the measure spaces. And I can define a new kernel, which is, you remember that Markov kernels are parameterized distributions on T and T prime. So I can define a parameterized distribution on T times T prime by just considering the parameterized ordinary product measure. And if I'm using these free floating dx dy, so if you want to have an equation in the normal sense out of this, then you can write an integral over an indicator function on the left-hand side and an integral over an indicator function on the right-hand side, and then it looks very familiar. So now I have the need for sequential composition. That was in my example with the discrete Markov chain. That was just a matrix product. And now it will be by Chapman-Kolmogorov, the composition of Markov kernels. And the composition is proportional to, so this is representing the joint measure, but then I'm integrating over the y coordinates. So I'm integrating the intermediate state out. And it's useful to have a notion of what's the identity map for this, or what's the identity for this composition. And that's just the Markov kernel, which if you're an X, you're moving again to X deterministically. That's a Dirac measure in X. So because at times we are not really interested in the composition, which in the end will create the composition between P and Q that creates a Markov kernel from S to U, but sometimes we're interested in the joint measure. So to have it a bit easier, I'm introducing the notation for the joint kernel, the kernel which represents the joint distribution on the product space TU given my current position in S. And
Moritz,
yeah,
can I interrupt? So there was a bit of confusion about that question, and your co-author Frank says you probably did mean 0, 1, not 0 infinity on that previous slide. Is that right? Just for
yes, that must be right. I didn't see the infinity at all. Yes. Thank you.
Thank you.
So now I have I just wanted to say that I can equally represent the product measure as a composition of 3 Markov kernels. And the first kernel is the first Markov kernel B, but then I'm composing with a duplication kernel, which goes from S from t to t times t. And the duplication kernel, what is it doing? It just creates 2 copies of the input. So when you have, if you think in samples, which is always nice, then if you had 1 sample on the space S, now you have 2 samples on the space S, and they are the same. And I'm keeping 1 sample, and I'm applying Q to the other one. So this is a different way. So the left-hand side, that's the notation which comes if you're starting from probability, and then the right-hand side is maybe the synthetic one. So I want to consider these Markov kernels not only composing with each other, but I also would like to use them as actions on distributions, and so that would be a push forward where I take a distribution and apply the Markov kernel. And applying the Markov kernel to a distribution is exactly the same as what you would get if you represent your distribution by a kernel from the terminal space to S. So that's the push forward of the Markov kernel P acting on the distribution. And then there's a bit of things what we want to observe, and let me say it in words first. So the issue I want to say is that a probability measure on pairs is not the same as a pair of probability measures. But if my measure I'm applying a product kernel to is of product form, then I can apply each of the elements of the pair to each of the elements of the pair and take the product of that. And if you think about what this means for the action, then it's related to the functor on the category being lax. So like I had now the action on measures, I want to have the action on functions. So now I'm taking a function h on t, and I define, as you would expect, ph as the pullback of h under the kernel. And if I have both, then I'm getting something like a scalar product, which plays the same role as the denominator in my example where I was computing row vector times column vector. And now it's measured composed with a function, and that's just the expectation of h under p. So for what comes next, I also want to have densities, and now I'm in a non-synthetic way, I just know about probability measures, what densities are, and I'm introducing the notion of absolute continuity. So if X is Q is absolute continuous with P, that just means that the measure Q is 0 on sets where the measure P is 0. So this for measures, and if I have probability measures, then this is equivalent to that Q has a P density, so that there's a likelihood ratio dq dp, a function from E to R plus, such that I can write the measure Q of, or the probability of a set A as integral under the probability measure P over the dq dp function. Or short, if I don't want to write the arguments, I'm using the dot notation again. And then for later use, I have given a very simple example where the Gaussian measure is obtained as a likelihood ratio with respect to the Lebesgue measure. So now I want to reformulate base rules in these terms. So I have two Markov kernels, or maybe the P is a measure because it starts a distribution because it starts from the terminal object. And then Q goes from S to T. And I assume that the Q has a, that's the kernel, but I assume that for each X, it has a, it's dominated by the reference measure lambda, for example, the Lebesgue measure. And to formulate things easily, I also assume that there are two random variables from some probability space into the product space SS prime. into the space ST. This should be here a T with the joint distribution, so that X has the marginal P, and then the pair X, Y has the joint distribution P dot Q. Then Bayes' rule essentially says that I have a likelihood, and I'm using again H, which is the density of the transition Q with respect to the reference measure with the Y fixed. And then I can give my conditional distribution P star given Y is equal to Y as it's defined by the measure P star has with respect to P, the likelihood ratio H over PH. So that's exactly the same as, now let me go back to the very beginning. So that's exactly the same as the definition of P star here. Only that it's local. Okay, so now I want to make some connections to other things. So this is the H transform as a variational optimization problem part. So let me first define the H transform. So I start with a Markov kernel P and function H, which I call these positive functions effects. So it's function H or likelihood function on Y. And I'm using this to give the kernel P a weight for each Y. And what you see there in the denominator is exactly what you need to put there to make P star a Markov kernel. So note that the normalization constant of a Markov kernel changed by H, that will of course depend on X. And then it's not surprising that you get as normalization constant the pullback of the function H under P. So and then I'm introducing, that was essentially the messages from before. I want to write that P star is M dot P, where this is exactly this function. So you have already seen that these H transforms turn up in Bayesian inference. And I want to give a second example. If you take now the setting, you have a measure Q on S and Markov kernel P from S to T. And you give me a measure mu, which is absolute continuous with respect to the PQ. So that's a measure times the kernel. That's the marginal distribution on the T space. And I'm using as function H as effect the likelihood ratio of d mu dqp. And my claim is that this transports the measure Q into the marginal mu. So if Q is composed with P star, I'm getting mu. This is how I have to change my kernel to turn it into a machinery which push forward the measure Q into the measure mu. And one can easily convince ourselves by that, just writing down the definitions.
Sorry, do you mind saying where the domains are and everything? It's hard for me to keep track of the X's, Y's, ST's, and A's and things like this. Where does mu live?
Mu lives on T.
And what is P star?
P star is, from the previous slide, the kernel which is changed by H.
Which lives on which space?
It's a Markov kernel from, in this case, like P, from S to T.
Oh, I see. So it's not like going in the other direction. It's in the same direction.
No, I'm going forward still.
Okay, thank you.
Thank you. And that's how it applies to Q, which is on a measure, a distribution on S. So So these effects are functions, and I want to put them a bit in context of the Markov category. If you have a non-causal Markov category, then you can represent these effects as non-Markov kernels. So if you have a non-Markov kernel from T to the terminal object, then you can associate with the function H with the yes, it's not a probability anymore, but this is a transition from Y into the set 1, which is the one element of I. And you see that if you restrict your attention to only Markov kernels, then the terminal Markov kernels are trivial. They cannot represent functions. But if you allow for non-Markov kernels, then you have this understanding of effects as part of the category. And if we have that, then we can consider this H transform. So I'm having a morphism P and I'm turning it into P star. That is given by the following string diagram. So if I have P, I'm duplicate and I'm giving a weight to the outcome by H, because now I'm using H as a weight on a space. That's the same as applying the morphism P star, but first making a kernel and giving the weight PH. If you morally, what you would actually like to think of is that this is multiplication of H times an element of the image of P, so in T, and this is division, but I'm putting it on the other side of the equation, so it becomes multiplicative. But so this way you can think of P star synthetically if you want. Okay, so now the connection to optimization. I'm introducing the Kullback-Leibler divergence. It's just my notation for Kullback-Leibler divergence. It's the integral over the log density between some Q and some P. And if Q is dominated by P, then I can integrate and I have this density. And if not, then I'm setting it to infinity. So you think of this as an asymmetric distance, and the distance is infinity if Q is not dominated by P. So if this likelihood ratio does not exist. And if you do the same thing for Markov kernels, then they are still measures with an index. So the Kullback-Leibler divergence still has an index. And a different name for Kullback-Leibler would be the cross entropy. And it's X dependent if you do it for kernels as parameterized measures. So I have a proposition, and that's Donsker and Varadhan's characterization of the H transform. So if I have an effect on H, and I want one which has a positive, so this is a scalar, and I want to be a positive because I want to be able to divide by P times H. That's like the row vector times column vector, a number. And the statement is that the logarithm of the PH is attained as the supremum over all measures dominated by P, or all kernels dominated by P, of objective which has two terms. One term which penalizes distance of Q to P in terms of Kullback-Leibler, and one term which asks for, if you think of the H, that's a likelihood. So this asks for the log likelihood to have high have high expectation under the Q measure. It's a trade-off between not being far away from the prior and being close to the it's also having high likelihood, if you think of it as a statistical problem. And then the supremum on the right-hand side, that's actually attained by the H transform. So the P star, that's taking the kernel, the Markov kernel P, and giving it a weight H over PH. That gives me that gives me the optimizer Q of the expression above. So for example, this tells me that posterior distributions, if I do this entire thing not with Markov kernels, but for distributions or for morphism from the I space, that my posterior distribution solves an optimization problem. How do you see this? So this is just Jensen's inequality. So if Q is smaller than P, so if Q is dominated by P, then I can write log PH, that's the log of the expectation of the effect H under the P measure. And I'm just expanding the one multiplying, no, introducing an X of a log there. So nothing has changed. But now I have the log of an expectation of an X. So I can use Jensen's inequality to say that this is larger than the E expectation. So that should be a bold-faced expectation of log H under Q minus the expectation of the log dq dp under Q. That's just the Kohlberg-Leibler from P to Q. So that's the first part, minus some technicalities which happen if one of the sides are infinity. And the part that I get, let me go back to the slide, that the H transform is the actual optimizer of this problem. The second part is, so if I look at this expression here on the right-hand side, if I'm using Q as P star, then this expression is constant, equal to log times a scalar number. And for constant functions, Jensen's inequality is not an inequality, but an inequality. So that's how I see that this is the optimizer. So I want to connect. I now have an optimization problem. And optimization problem tells me then very naturally how this H transform should compose if I'm using it on a composition of Markov kernels. So now I'm having a space S0, a kernel from S0 to S1, that's P1, and then from S1 to S2, that's P2. And to have a lighter notation, I'm just fixing the starting value. So that's somehow an X0 from which I move from S0 to S1, and I keep it fixed throughout. And so then P1, 2, which is P1 dot P2, that's my joint probability on the S1 times S2 space, induced by the transition from X0 to S1 and then S2. So if I have a likelihood, and it's really a likelihood on S2 or an effect on S2, which corresponds a bit to observing a process at end time, only that I have now only two transitions. And then I can look at my H transform, and I know that the H transform will be the optimizer of the Varadhan functional. So this is the thing which characterized the P star if I find the optimizer Q12. And Q12 is just a measure dominated by P12, but I can write it as a product measure, just like I have written the P1, 2 as product of a marginal and a conditional. And now I can rewrite this objective into, it's a supremum over Q1 and over Q2. And I can rewrite this into a supremum over Q1. Then I collect everything which depends on Q2. And I can solve this optimization problem first. And whatever I get, I can use it to determine Q1. So this is the Bellman principle. The first best step, so the best choice of Q1 to maximize the objective here, is the one which maximizes the overall objective if it's followed by an optimal remaining step. So if you want to go in an efficient way from A to C via B, then part of it is moving very efficiently from B to C. And now this will be a bit too technical for the talk, but I would like to have it on the slides and just mention how it works. So if you want to solve this optimization problem, then Bellman invites you to introduce the value functions, and these are defined backward recursively. You start with the H2 function, and then the V1 is the optimizer over the Q2, and the V0 is the optimizer over the Q1. And you get these local optimization problems backwards in time. So, but that's just the start. So I can figure out what V1 is. And if I then look for the maximizer, which is here, this is just of the Varadhan form. And it just means that my optimizer Q2 is a transition kernel, which is an H transform. Note that H1 here is defined as, sorry, the L is a typo. It should just be H1 is equal to P2, H2. So my optimal choice for Q2 is a H transform. And if I use that information, I get also that my optimal choice for V1 is an H transform. But now it's an H transform, not with the previous H function, but with the pullback. So I'm transforming with the pullback and not with the original H anymore. So the H1 is the pullback of the P2 of H. And this already introduces the bidirectionality. So I have these two kernels, P1 and P2, and I'm looking at the composition. And I said that the P1, P2 star is equal to the P1 star, composed with P2 star. And the P2 star was the optimal solution to an optimization problem. And then the P1 star was also the optimal solution to an optimization problem. But you have to be a bit careful that the P1 star has a hidden dependency, because it's not H transformed with H2, but it's H transformed with the pullback of H2 under the P2 kernel. So that's important. Maybe I should be a moment slow here. So and now you get this optical structure. So you take the H, you pull it back to the P, you have the message M, you push forward the marginal conditional, and you get P times P star. And if you look at the composition model, then it will be exactly that. So you're going one step back, sending a message, and now you're doing the H transform, but not anymore with H2, but with the pullback. And you're sending the message, and then you're transforming the P1 with the message M1, that you get your P star 1, and the P2 is the message M2 gives you the P star 2. So this composes optically. And I want to skip this part, but I want to say one thing which is relevant. I have no time to talk much about the Cartesian structure, but one thing I want to tell you, and that's that if I have effects on the product space, which are multiplicative, so if I have a product effect H2 times H prime, and it comes after a product kernel P times P prime, then I can simultaneously compute it as first applying P to H and then applying P prime to H prime. And I also want to introduce the notion, or invite you to think about the notion of fusion, and that's the pullback of product effects. So if you have looking at the string diagram going from the bottom to the top, and on the top it's closed off with two effects which have product form. So it's H times H prime. and I'm interested in the pullback under the duplication dot black dot operator, then this is just the product of the H functions evaluated in the same point. And you have seen that before. If you ever multiply two Gaussian distributions with different, so the densities of Gaussian distributions with different covariance matrices, then you will end up with either the expression for the new covariance matrix of the distribution with the density proportional to the product of the densities, or with the Woodbury formula. So you have seen this in Kalman filtering, for example. So let's go through this example, and that is classically Kalman filter is related to a state space model, where you have given a starting state, a latent Markov process evolving discretely in time, and emitting observations y1, y2, y3. And now we can reformulate this as a string diagram. So we have these transitions, and I'm calling the transitions of the latent process P1, P2, P3. And the transitions from the latent to the observables P'1, P'2, P'2. And there you get it if you now use generously the copy kernel. Then you can write down the transition of the starting state x0 into the joint measure of the observations. So if you can do that, then if your H is of product form, so if it's a function which is a product of some H1 evaluated in Y1 times H2 evaluated in Y2, etc., and this will be exactly the case if you have conditionally independent observations, then you can back filter, and then you can write down the optical structure where the backward pass is pulling back the H through the kernels, and the forward pass is pushing, and they're doing the left-hand side. So I have maybe a few more minutes, so then let me just say a little bit about so we want to use this in practice, and we want to think of it as a way to automatically transform a program given in some way into a conditional program. And there are some things I want to make think of them as concessions. And the first thing is sometimes it's just too difficult to find the optimizer. But you can consider the following. Just don't look for the optimal choice in the class of conditional distributions which are dominated by P, but just look in the optimizer in a subclass. So that is variational Bayesian inference, or variational optimal transport, or something like that. And yeah, from this, you can already anticipate that it composes optically, because you're just doing optimization problems by Bellman's principle. It still works, but you're now optimizing in a subspace. Still, Bellman's principle tells you how things should compose. And then the second choice, and that's, I think of it a little bit as a version of the, do you know the A* search algorithm, where you essentially, you would like to know the shortest way from your current position into the goal, but you don't know this. So you use a heuristic instead. And here you can also, if you don't have the H transform, because you cannot compute it, you can use a heuristic H tilde. And if you use H tilde, then you don't get the P*, but something else. But if you have that else, then you can look at the corresponding change of measure, which gets you the P* from the P circ. And this change of measure is surprisingly tractable, even if it you would expect it to contain things which are uncomputable. So I don't have any more time, so let me just skim shortly over what has to stay topic for another time. So I have here in the slides just showing that you have seen that you can compute the push forward, the optimal transport, and it turns out that optimal transport solves the same. It solves the same type of optimality criterion as I had before, so a Varadhan type of thing. And then the second thing is what I wanted to say is that we also have a theory which we can use where we are replacing discrete time transitions by continuous time transitions. So you can do the entire thing for continuous time Markov processes, and you essentially get composable transition laws. Essentially, you can combine it if you have a mixed model where some of the transitions are corresponding to continuous processes, or some of the optimal transport problems are described in terms of continuous processes. And then I have some slides here about this. And now I want to finish with giving you some references. So part of this is in the a bit outdated paper on arXiv. So this is automatic backward filtering, forward guiding for Markov processes and graphical models. That contains the core ideas here. Then before we were thinking about the compositionality of this procedure, we were writing the continuous discrete smoothing of diffusion paper. And that is essentially a similar thing, but not yet thinking about compositionality. And then there's some further references where we consider continuous time Markov processes and a short introduction into the topic. So thank you.
Great, thanks, Moritz. Let's give Moritz some round of applause, and then we'll get some questions. Okay, we've got a hand up from Lee.
Yeah.
Oh, yeah. Hi. Thanks for that terrific talk. I had a question, as I often do, on applications. I was wondering, how much direct application you and your group have with all the many applications of so-called Granger causality work, which has, been around for a number of years and is very much involved in, in this whole domain of applications in medicine and finance.
Maybe this is, I have no personal connection to Granger causality. So I can think about if there's something, but right now I haven't used it in this way.
Okay, thanks. I was just curious.
Yeah.
I guess I can ask, can you say a bit more about what you have in mind for continuous time Markov processes? Because I have this idea that when you're using category theory, you're kind of inherently discrete time, like a morphism in a category is inherently a kind of discrete time step by default.
Yes. So I have to move some things away that I see where I am. Yes, I'm here. So the starting point is that I'm just considering a continuous time process. And so for continuous time processes, there's not anymore this transition matrix, but I could, or this transition kernel, But I could look at the families of transition kernels from one time point to the next. But the easiest way to characterize it is in terms of the space-time generator for this purpose. And this is a device which tells me if I'm looking at the difference of a time-dependent function evaluated in the Markov process, what do I have to subtract to make this expression a martingale? So typically for some f, which is time dependent, if I'm looking how this changes, if I'm evaluated in x changing over time, that will not be a martingale. But if I subtract the right function, then it will be, and I can call this function as the image of this space-time generator AF. And then it just turns out that, yeah, well, so just if you want to embed it into the larger picture of a discrete vault and transitions, then this continuous time process could be a model for what happens in a transition along a certain edge. So instead of saying that I'm moving from S to T, you say, okay, I'm moving, but I'm moving along this continuous process and just taking the end value at time T. That then is just a Markov kernel. But it's still nice to look at this because you can still say something about this transition. And the thing you can say is that there's still optimization problem which describes how the conditional process evolves. So you have the discrete conditional process which evolves, and you can figure out how it does by using Bellman principle. And then in continuous time, you can describe it by a Hamilton-Jacobi-Bellman principle. So essentially, we think of continuous time processes as devices to get particular interesting transition kernels.
Thanks. Yeah, there's some stuff to think about. I think what you're saying is the same kind of ideas I vaguely had in mind, which is like continuous time can be thought of as a whole bunch of discrete time things between choices of time snapshots, but they have to patch together in the right way.
Yes.
Which is
you can take a meaningful limit there. It's even that the fusion was multiplicative, you remember? So if you have the fusion of information, you get a multiplicative element. Mm-hmm. And you see here an integral and the exp. So here you're fusing in information, but in a continuous way. So this part is a continuous version of this product here. So it's even more connected, but their category theory, I know, is I cannot describe it, but I think it's more than just saying there's a transition there. It's stronger linked.
Thanks.
Okay. Well, I guess we're out of time for the kind of recorded part of the meeting. So I suppose we can go off the record if there's anything.
Thank you. I know not going off the record, but for having me here, and I'm still here, so now we can.
Yes, great. I mean, it's been a pleasure to hear.